This video is something a little bit different to what I normally do, and it's all about the EV transition of vans and HGV. And if anybody knows who's in the industry, it's a really big challenge. I'm going to show you a EV transition tool which really can help. People are going to be amazed. I'm going to turn the mundane into magnificent. And this particular EV solution is called Zero. It's from Dynamon, and I know that this tool could help so many commercial fleets and help with their transition, save money, make sure it's fit for purpose, whether it's EV selection, deciding on which routes to electrify first, and also the infrastructure, which is so crucial to make sure that your BEV vehicles have enough charge to complete operations. And this simulation tool does all of that all in one. So let's get into this without further ado. So what we've got here is our Zero EV transition dashboard. So this here is just got a few bits of information from real world data. So let me just take you through it. It might look a little bit complicated, but I'm going to take you through this and your mind will be blown. So in here, we have got real world data from a postal operation of 7.5 ton vans. And it's 2 locations, so 2 depots where the vehicles are operating. There's 25 vehicles within this operation, and we've got 72 days worth of driving data, which has given us nearly 250,000 miles worth of analysed information, data. So where do we get this information from? So there's a couple of ways. You can either get your fleet data and input it manually yourself and create a synthetic data, or in this case, this is real telematics data. So we can work closely with your telematics provider, take the information through an API or a CSV file and put it into the system. And why this data is so important, because it gives us all the information that we need to understand where these vehicles are going. So this is ICE, so internal combustion engine vehicle data. So understand where they're going in terms of the landscape. Is it flat? Is it hilly? To understand the efficiency, where the dwell times are. What I mean by dwell times is there a potential opportunity to charge them at the depot or elsewhere where they're not just stopping to charge, they're charging while they're stopped, which is absolutely key. So we're not affecting the operation and we're minimizing downtime. Right, so as I mentioned, we've got locations, vehicles, the analysis of the data, 72 days worth of data, although this system can take up to 12 months worth of telematics data. So which is really quite key for businesses that have seasonal fluctuations, because there might be more vehicle routes, more complicated operations. So it's great that you can put that information in there, and we can put up to thousands of vehicles into this system. Not only that, but we can put in hundreds of locations. And very quickly with this software tool, we can understand, if you're at the beginning of your transition, you haven't started yet, this is a really good software to understand, where do you start? I mean, it's such a complicated thing, EV transition. It's like, I've got a 500 vehicle fleet. Where do I start? So this system can help you understand, which locations to electrify first, which routes to electrify first. So let's go into the detail. So what we've got here, we've got the fleet composition, which basically means this can deal with not just one type of vehicle, but a mixed fleet. So not just vans, but vans, HGVs, tippers, cars, all the different types of vehicles. In this case, it's only one type of vehicle, so we're keeping it simple. Vehicle in service dates. So why this is important is to help with your EV rollout strategy, which essentially means when, you don't want to transition all your fleet to electric all at once. Not only is that going to be extremely costly, but also, you might have vehicles in the operation that don't need changing yet. So we put all the ICE vehicles in terms of when they're due to come off. And this helps to iron out those peaks in terms of cost, in terms of reducing that CapEx cost. We've got the average daily driving distance of each depot. So depending on where the vehicles are stationed, that will give us an idea of the average daily driving distance on both sites, Birmingham and Bristol in this case. And we've got what I see as one of the most important tables, which is vehicle utilization report. Green, this shows when the vehicles are driving according to telematics. And the telematics is great because you can see the latitude, longitude, where they're going, what speed they're going, the topography, the geography, to help understand the efficiency of these vehicles. Because there's so many factors that affect the range and efficiency of your electric vehicle. And I'm going to go into a bit more detail with regards to weights, etc. in a minute. Dark blue is stopped at a known location. So that'll be one of the depots that we've added into the system to understand where the opportunities for charging are. And then orange is stopped at an unknown location. So that could be one of your drivers stopped for, a job or for lunch, hopefully not the pub. Let's hope not. So let me just show you in terms of the keys here. So we've got locations and vehicles. If we look at the locations, we've got both depots here. We've got Birmingham and Bristol. And here we geofence them, which basically means that we put a fence around your depot location to understand from the telematics when these vehicles are coming in and out of the operations and where the dwell time is for opportunities for charging. But not only that, it also helps with the infrastructure side of the software to help us understand where the peaks of energy demand are. So understanding, have I got enough energy in those peak periods? So that's why we geofence them. Vehicle setup, it's just all the detail of the vehicles that we've put in here. So the ICE vehicles, internal combustion engine, and you can group them as well. Journeys, this is the synthetic routing to manually add the telematics, which is what we use in this example. And we've got an EV database, which you can select a vehicle, an electric vehicle or BEV, to simulate against the ICE data. So what we're doing is we've got the normal diesel vehicle, if you like, van, and we're simulating an electric vehicle in that footprint of its daily operations to understand, is it going to work? Is it going to run out of range? Is it going to run out of charge? Or is it going to be fit for purpose? Now we've got loads and loads of vehicles in here, probably got 90% of all vehicles, specifically sort of the vans, trucks and buses side. So you can actually add a vehicle very simply. So you can put in the vehicle class, manufacturer, make, model, trim, weight, battery capacity, model year, price to understand TCO, the total cost of ownership at the end, any additional information, the dimensions, charge specification, because not all vehicles, when you're talking about AC charging and DC charging, to understand what the vehicle can actually take on board in terms of charge to make sure it's accurate when the feasibility of that vehicle working in the operation is there. You've also got the tire and aerodynamics. So tires make a huge impact in terms of the range because the rolling resistance does change. And Dynamon, before the Zero EV transition tool, they are heavily involved in analysis of how tires and aero can help improve the efficiency and save businesses money. Charger configuration. So these are the different charger powers that we can put in. But let me just go back to the dashboard just to give you a bit more of an understanding of why I'm talking all the way through this. So we've got here the simulation that I've configured against the ICE fleet data. We've got, you can put up to 3 vehicles in here. So against the ICE data, I've put 2 Iveco e-daily vans of 2 different battery sizes, 74 kilowatt hour and 111 kilowatt hour, and also a vehicle called a Magtech, which is 120 kilowatt hours. We've also configured 3 different charger speeds, 7 kilowatt hour AC, 22 kilowatt hour AC, and 50 kilowatt hour DC. And then just below here, this is just high level analysis, and we'll drill deep into the granular information in a minute, which I think you'll be pretty amazed at. But this is just high level, where what we're going to do is zoom out here. We see the 2 depot locations, Birmingham there, Bristol there. We can select a particular vehicle, and then we can select a charger speed. We can also change the temperature. And as anyone will know that's up to speed with EVs, is the temperature, whether it's winter or summer, makes a huge difference in terms of the efficiency. It's normally about 20% between, normal ambient temperature versus harsh. It also can help you understand the battery degradation if you want to simulate that. So if we apply that data, and what we've got is a score out of 100 or score out of 10 here. Green is easy to transition, yellow challenging, and red is difficult to transition. So 96% for Birmingham at that particular configuration. That's really, really good. Bristol, 65, not so good. So how can we affect that? So what we can do is we can pump up the battery size to increase the range, see if that increases these percentages here. Okay, great. So Birmingham's gone up 3% and Bristol's gone up at 20%. So does Birmingham really need the bigger battery size vehicle just going up 3%? You know, is it cost effective? Are we optimizing the EV selection in that particular example? Well, we can drill into the data and find out in a minute for EV selection and the charging speed. So we've got, probably could do a bit better on Bristol. So let's improve the charging to 22. Okay, great. I mean, Birmingham's 100% now. Bristol's 96%, which is great. Let's change the vehicle to 120 kilowatt hour battery magtech. And a lot of people might think bigger battery, it's going to go further. Not necessarily the case. It all depends on the efficiency of the vehicle. So let's just apply that. Okay. Birmingham's similar, but Bristol's gone down to 42%. And if we remember, the daily driving distance of the Bristol depot vehicles were a lot longer. So clearly the magtech's no good. Okay, well, let's just improve the charging. Let's just put a bigger charger in there. Apply it. Hasn't changed at all. So this is really, really useful to understand before you start putting money into the EV infrastructure, before you start buying the vehicles, to understand and simulate accurately. That is the key to work out what is going to work in terms of EV selection and infrastructure. Let's drill down into a little bit more information, but just before I do that, so just as a bit of a recap, what this system takes into consideration is the tire, the aero, the vehicle efficiency, the weight, and also the cargo weight. So something that I didn't actually show you, when we're setting up the vehicle and selecting them, we can actually change the cargo load. So up to 100%, for example, or we can put on a refrigeration unit or a PTC heater. So anything that's going to affect the efficiency of the vehicle. We can even specify charging curves on the charging. The charging curve will start quite high if it's got a low state of charge, SOC, and then it will tail off towards the end. Generally speaking, use of charge curves really, really helps, again, to be accurate, to give us the insights that we need for our EV transition. So let's drill into the detail now. So what we've got here is the EV transition plan feasibility. This is where we can select a location. We'll go with Bristol because that was the challenge. Again, we can change the different vehicles, the temperature. We know that the magtech's no good, so let's just take that out by concentrating on the vans. So what we've got is the two different vans at the top, two different battery sizes. We've got the chargers along the left there. And this bar graph is showing us green for completed days and red for incomplete days. So when we simulated this vehicle with that charging in the operation, this is the number of simulations that have passed without failing. So not running out of range, basically. So what we've got here is 22 kilowatt hour, bigger battery. That's a really good percentage. That's 95.5. Going up to 50 kilowatt has only brought it up by 3%. And a 3% increase in feasibility for the sake of 50 kilowatt DC charging. If anybody knows the cost of going higher in charging speed, it can be quite expensive. And it is especially expensive when you go from 22 kilowatt AC to 50 kilowatt DC, because a 22 kilowatt AC charger is about £1,000, whereas a 50 kilowatt DC charger is just over 10 grand. Plus the fact that you need more power, which might cost you more money, and also more infrastructure, thicker cables, that sort of thing. But what we're going to do, we're going to drill into the data on the 22 kilowatt AC charging and that particular battery by clicking on this bar chart. So what we've got here is each individual vehicle where we've simulated it, and it shows us the number of completed days as a percentage. So state of charge on the left, completed days on the left, and the vehicle, in this case, registration numbers at the bottom. And as you can see, there's a particular vehicle that stands out like a sore thumb, 61% incomplete days. So let's click on that particular vehicle. This is where it gets really clever, because what you can do is we can look at every simulation on a daily basis where the software has simulated this vehicle with that charger speed against the normal ICE data. So what we've got at the top here, we've got start, date and time, distance traveled, total time, total journey time, total stopped time, completed, lowest state of charge, and final state of charge incomplete. And on this particular one here, we've got minus 19.9%, which essentially means that definitely didn't work. So let's select that particular example. So this is where the magic happens, because we've got here the state of charge graph on this particular day, this particular vehicle simulated with that vehicle, that charging. we've got here the map showing us where the vehicle goes and the state of charge. So we've got state of charge on the left, time at the bottom. So here it is at depot down in Bristol, charging up to 100%. And then at 1:30, off it goes on its normal operations. And then it comes back to site and there's an opportunity to charge. It's there for half an hour. So it charges on the 22 kilowatt charger up to 84%, and then down, off it goes again. So draw the battery, 15-minute opportunity, charges, then off it goes again. Then obviously someone stopped at a job or a long dinner, and then off it goes again, charging. Then as it gets into yellow orange here, that's under 20% state of charge as a bit of a warning. And then red is dead. And it's great to see that. It's great to understand that that particular vehicle on that particular day, in that level of detail, we know that that doesn't work. So what do you do about it? And this is, again, why this system is really, really good, because you can actually change the configurations to make it work. So a couple of things that you can do. You could change the vehicle. So we could try and find a vehicle with a longer range that can still cope with the cargo load and all the other factors that affect efficiency. Or in this case, well, let's change the charging. So let's up it to 50 kilowatt DC. So now the chart has changed. And when it came in for its charging during its dwell time, when it was loading or unloading, it's actually charged twice as quick. And now that means that the state of charge got down to 9%, which is pretty low, but we have been very accurate in terms of the cargo load and all these factors, even the temperature, because we're in winter. So we can be confident. And that is the key here, being confident that what vehicles I'm buying, the infrastructure that I'm putting in, big cost, that it's going to work. What if the company doesn't have the money for the 50 kilowatt charger? Or more likely, they haven't got the power, because power is a big challenge out there in specific areas. So let's go back to 22 kilowatt DC AC charging. So what are the other options? Okay, so what you can do is we can overlay public charging. So rather than putting money on your own charging, you can utilize public charging. You can even specify a particular network. So you might have a Shell BP card All-Star, or you want to, deal with a particular charge point operator, CPO, or in this case, we'll just put them all on there. Happy days. So what we can do quite easily is we can understand, okay, well, where is I'm just going to zoom in to make it a bit easier. So where does this vehicle get low in charge? So we know this road here is clearly getting low in charge here. There's a charger on the way, so that will help minimize downtime. And it gives us all the information we need. It gives us speeds of chargers, whether they're operational, and even the cost, 79 pence per kilowatt hour. So not only can you do this, but we could also, and this is a hot topic at the moment in the EV industry and commercial fleets, we could simulate a shared commercial charging site. Because not all vans, and especially not HGVs, can charge at your Tesla charger or your Shell or what have you. Interval, other brands are involved and available. So it's really nice to know that now there's a lot of work being done in the commercial charging space, shared charging, and there's so much going on at the moment. So we could simulate a shared charging specific site specifically for commercial vehicles to help increase that feasibility, to make sure when we're simulating particular electric vans or HGVs that we can make them work. So that is the EV feasibility side of things and fleet operations. Now, there is a lot more to this system, but my voice can only stand so long. So I'm going to now go into the infrastructure design tool, because these two elements of the software are absolutely key. The thing is, not many companies put it all together. It's like, okay, the fleet department, they're buying the EVs, they're selecting the EVs. Oh yeah, they're going to be fit for purpose. And then you got the property guys, and they're sorting out the infrastructure, but it's not coming together. And it's absolutely important to understand, well, yeah, okay, those are the vehicles and they work, but what's going to be the energy consumption? What are going to be the peak energy during certain days? And this system allows you to simulate that. So we can, in this infrastructure design tool, we can select the location, depot location, different vehicles as well. We'll stick with the one that we're in. So there's 12 vehicles in this depot. We can change the battery usage from typical, heavy to maximum. So the maximum would be the most energy that vehicle consume during the whole of the data. but there is an option now, a new feature where we can go into specific days. I'm not going to show you today. I'll maybe show you in another video if we get lots of traction on this video and we get some comments, and I can show you in a bit more detail how we do that. So let's stick with heavy usage. This is location energy consumption. So that's the whole, all of the vehicles. And just here, we've got a graph which shows us where the vehicles are, whether they're in the depot or out of the depot. So I've got time at the bottom, vehicle count on the left. And again, that's really crucial to understand peak energy demand. In the location configuration, we can swap it between kilowatt and kVA for site fuse limit. I'm going to put it at 100, which is pretty low, because I want to demonstrate where there's not enough power. Varying base load we can simulate. So let's say that your infrastructure partner, prior to spending all the money on infrastructure and EVs, I would always recommend to get a site survey done first to understand how much power, so your site fuse limit, and also your varying base load. So your future chargers or your chargers right now might be using the power from the depot, and that depot power will change if there's a lot going on in that depot. For example, if everyone turns the kettle on at 8:30 in the morning, that is going to reduce the amount of power that you have. So this is a way of simulating that on a 15-minute basis. You've also got charger configuration, so we can specify heavy usage, again, temperature, charger efficiency. Average is normally 94%. So there's a little bit of loss between the DNO, the grid, and getting it into the vehicle. Time charging, this is absolutely vital in terms of trying to reduce costs. So let's say you've got your car and you're benefiting from overnight charging. Loads cheaper. Now, it could be the same in a commercial vehicle operation for charging your fleet. So this is a way to change when your vehicles charge from, which has a massive impact on your infrastructure, because you want to make sure that your fleet is charged fully so they can continue with their operations to make sure it all goes to plan. Now, if you're charging in a smaller window, it might be the fact that you need more chargers and you might need more powerful chargers because, like I said, you've got that smaller window to be able to charge your vehicles potentially. So you do simulations, one without time charging with a fixed rate from your electricity provider, and one with a variable rate and use the time charging. That's, again, I can do in another video if people are interested. Whack it in the comments. Charger management level. So we can simulate no management, which basically means from the telematics, it's telling us, okay, when the vehicle comes in, it gets on the charge. And when the telematics tells us the vehicle has left the depot, it comes off the charger. With managed, that charges the vehicle up to where it needs to be, and then that charge will go into another vehicle, even if the other vehicle's not left the depot that was originally charging. We've also got static limited load management. So what we've got here is this is all about optimizing number of chargers, because you don't want to buy more chargers than you need, and you don't want to go higher on the charger power than you need, because again, it's all about optimizing, saving that money. So what we're going to do, we're going to put in 22 kilowatt chargers, 12 for the 12 vehicles. I'll come to site battery storage in a minute and ignore fuse limit. We'll apply the changes. So I've configured the location. We know where the vehicles are. We know how much power they're using. We've done our charger configuration. We've applied the changes, and that gives us an understanding of the power demands, which is just below here. And this black line is showing us our site fuse limit. So I'm just going to change it to unmanaged charging. There we go, just for this demonstration. So only 7 of the 12 AC chargers are being used, and only 6 of the vehicles are being charged out of 12. And I know the reason for this. It's because there's not enough power. So if I click ignore fuse limit, so let's pretend we've got all the power in the world, apply the changes, you can quite clearly see we've got the black line, which is the site fuse limit, and the power demand is going above that. Not only is it showing us that we haven't got enough power, it's showing us how much power we actually need more than we've currently got. So we've got 100 kilowatt fuse limit, and 220 is what we need. So, okay, so what do you do in that scenario? You go to your DNO, and they take about 30 days to respond to you. They're not the quickest, but I know they've got a lot on their plate at the moment. And it might take years, in fact, to get the power you need, especially if you need another substation, etc. So they might be able to give you 50 or 100 kilowatts straight away. So let's simulate that in a second. But just to show you, now we've got all the power in the world. Look, well, 11 of the vehicles out of 12 have fully charged, and we're utilizing more chargers, but we'll come to that in a second. So let's up the power. So the DNO has been very kind. They come back to us and they give us another 100 kilowatts. We apply the changes. Not quite enough for that peak now. We're 20 kilowatts away. So we've still got all the power in the world because I'm ignoring the fuse limit. So let's just work out what charges we need, optimize them before we look at the power. So let's up the speed of chargers because, like I said, they're not all getting fully charged. Okay, great. Now all 12 vehicles are fully charged. Now we've got some more powerful chargers, but look, the 22 kilowatt AC, we're only using 8 out of 12. So there's no point having them. So let's optimize that by changing it to 8. There we go. So we're all in the green now. All the chargers being fully utilized. All the vehicles are being fully charged, but we haven't got enough power. In fact, we're 54 kilowatts off now. Now we've charged all the vehicles and got powerful charging. So what do? The DNO, they can't give us any more power for another 5 years. So yeah, battery storage. Let's pop in a 100 kilowatt hour battery. You can change the discharge efficiency, charge rate, supply that. Great. Okay. I mean, you can play around with and reduce that down to save yourself money. Again, it's all about not overdoing it. All the time in my previous job, we're talking about future proofing. Realistically, it's all about optimizing. And this is really important actually, because this EV transition tool, realistically, you want to be able to analyze your whole operation. You don't really want to analyze just 50% or 20%. I mean, yes, you could do, but the problem with that is you put in the infrastructure for the 20% or the 50%, you might have to change it again. And and the charge companies will say this, dig once. You don't want to have to change all the cabling, all the charges again, because you didn't look long term. You look long term, you can understand, okay, well, actually I need this much power. And you can strategize, you can roll it out properly, save that money in the long term and not have to worry about changing infrastructure moving forward. So that's great. We've got the right chargers, we're optimized there, we've got the battery storage. And again, battery storage, you can take advantage of utilizing it when in off-peak times to make some money from your battery. And there's lots of companies out there to do that. We've also got just understanding from the graphs the battery capacity when it's being fully utilized and when it's got full charge, and also the charge and discharge rate. This is the tariff section, which I can take you through on another comment. If you put it in the comments, which I can talk about time charging, big savings there. So if I go to the TCO, which is our total cost of ownership. So this is in beta at the moment. However, what it does, you can put your current vehicle in there, your ICE vehicle, and the EV vehicle you're looking at, and all the costs, replacement cycles, and the efficiencies and everything else, and put a threshold in there, and that will help you understand when and whether it is viable for you to change your vehicles to electric. Is it going to be cost effective? So what we've got here is table of results. We've got a TCO overview to understand whether you should electrify your vehicles or not, and then a rollout strategy, which will tell you, okay, first year, 17 out of your 25. Next year, another 3. Next year, another 2. It might be the fact that it's not quite as rosy as this. This is obviously quite a rosy example in this particular case. But yeah, again, helps you strategize, helps you make the decisions in an efficient way using the data. And it's all about using the data. There is a lot more to this. We've even got a new feature, which is called the locations overview, which will help a business understand where is the best location to charge first, because you might have an operation with 500 depots and 1,000 vehicles. Where do you start? And again, this is what this tool is really, really good for. It's like, okay, where do I start? Like, let's get that data in, let's analyze it, and let's produce these insights which are valuable to make the right decisions in a cost-effective way that's going to be fit for purpose. So this system is a lot bigger. And Dynamon are working with really, big companies, big fleets at the moment, and partnered with many, many companies. I'm more than happy to share it and go into more detail. If you want prices, that sort of thing, give me an email at tim.aylen, AYLEN, at dynamon.co.uk, and I can go into more detail. If you really like this video, please comment. Thank you very much for listening. And if you want to tag me on LinkedIn, again, I'm on there as well. A little bit different for Chargeheads today, but like I said, really passionate about EV transition, and this tool is absolutely key for that. Thank you very much for watching, and I'll see you next time.